last video, we started talking about the graphs of functions. Now remember, a function is just some sort of a rule that assigns values in one set to values in another set. Oftentimes we describe functions using some type of an equation. Now we've also talked in the past about finding the x-intercepts and the y-intercepts of linear equations. Those are the points in the Cartesian plane where the graph of your line hits the x or the y-axis. It's not just lines that have x and y intercepts, all sorts of functions can have them. And we find them in the exact same way that we found x and y intercepts for lines. Remember, the way that we found an x-intercept is we wanted to figure out where the y-coordinate is equal to 0. Now, f of x really is representing the output, right? It's representing the y value. So if we want to set y equal to 0 for a function, we really just need to set f of x equal to 0. So set f of x equal to 0. And solve for x. So replace the left-hand side with 0, and then solve for x. Now, this is a quadratic equation, and usually we can try to solve this first by factoring. This factors because it's a difference of two perfect squares. 4 is a perfect square, and x squared is a perfect square, so it's going to factor to 2 plus x and 2 minus x. I set each one of these individual factors equal to 0. Set 2 plus x equal to 0, and then 2 minus x equal to 0. And solving this gives me x equals negative 2, and x equals positive 2. Okay, so these are going to be my two x-intercepts, namely at the point negative 2, 0, and at the point positive 2, 0. This function here is going to cross the x-axis. Now, to find the y-intercepts, remember, we have to do the opposite. Instead of letting the y value or the output be equal to 0, we let the x value be equal to 0. So set x equal to 0, and we'll solve for the output y. Or in this case, we could call it f of x. Another way of saying this is replace your x with 0, or evaluate the function at 0. So f of 0 is going to give you 4 minus 0 squared, which is 4. So we have a y-intercept at 0, 4. Knowing these two things is enough to give us sort of a rough idea of what the graph looks like. I can plot my y-intercept at 0, 4 up here. Let's label that with a 4. And I can plot my two x-intercepts at negative 2, 0, negative 2, and positive 2, 0, positive 2. With these 3 points, and knowing that x squared function is a parabola or a U-shaped graph, I can sketch in the rest of this graph as follows. It's probably going to look something like this. Okay. Now, these x-intercepts in particular can be really useful for us in finding all sorts of different graphs. We'll see, especially in calculus, why it's really useful to know where a graph crosses the x-axis. And so oftentimes we call this a zero of a function. Sometimes they'll even call it a different word. They'll use the word root, the root of a function, but we'll use the word 0. So a zero of a function is an x value such that f of x is equal to 0. Well, that's exactly what we did over here. We set f of x equal to 0 and we solved for x. So essentially a zero of a function is just the x value of an x-intercept. An x-intercept itself is usually written as an ordered pair, and a 0 is just the x value pulled out of that pair. So we would say that the zeros of this function that we just looked at in this example, the zeros would be negative 2 and positive 2. Those are the zeros of the function. Alright, let's look at another example. Let's find the zeros of x squared minus x minus 12 first. Alright, again, all we're doing is set f of x equal to 0 and solve for x. So I'm going to replace f of x with 0, and I'm going to solve for x over here. This is a quadratic equation, so the first thing I'm going to try to do is factor it. Okay, I need two numbers that multiply to negative 12 and add up to negative 1. Like this is like a negative 1 here. So 3 and 4 should work, and I want to be negative overall, so I'm going to put the negative with the 4. So this is factors to x plus 3 times x minus 4. Now I'm going to set each one of these factors equal to 0. Solving for this gives us x equals negative 3, and set 0 equal to x minus 4 and solve, I get x equals 4 as my other 0. So the zeros of this function would be negative 3 and 4. Now let's try to find the zeros of the second function here. Again, we set f of x equal to 0, and then solve for x. How do we solve for x here? What's going to make this equation true? Well, we could get rid of this radical by squaring both sides. We don't have to worry about anything funny happening here because we just have a 0 on the left-hand side. So I get 0 is equal to x squared minus 49. Then I can factor what's inside the parentheses to get, or I can factor x squared minus 49. It's a difference of two perfect squares, and it factors to x plus 7 and x minus 7. Setting each one of these factors equal to 0 gives me a solution of x equals negative 7 and x equals positive 7. So my two zeros would be negative 7 and positive 7. Okay. Other things that might be of use to us when we're looking at graphs of functions are the intersections of the graphs of two different functions. So let's say we wanted to figure out where the graphs of the functions f of x equals x squared plus 1, and then the function g of x equals 5x plus 7, where do those functions intersect? Where do they cross each other? Well, I can try and just do a brief sketch of this and get a sense of where these might cross. 5x plus 7 is linear with a y-intercept of 7 and a slope of 5, so it'll look something like this. And x squared plus 1, we'll see later in a later unit that this is a parabola that's been shifted up by 1. So this is going to look something like this. So we can see that it'll intersect at a point roughly around here. And then again, somewhere up here off of our actual picture, right? The line will keep going up, the parabola will keep going up, and they'll probably cross again. But how do we find the exact values where they meet? Well, keep in mind, we're trying to figure out for what x values do these two functions give you the same output. So for what x values is f of x, the output of the parabola, equal to g of x. That's the output of the line. To figure that out, we just need to set f of x equal to g of x, and then solve for x. Okay, so we're going to set these two functions equal to each other. So we get x squared plus 1, that's your f of x, is equal to 5x plus 7, that's g of x. And now I need to solve this equation for x. Well, this is going to end up being quadratic because we have an x squared term. So the way that we usually solve this is to move everything to the same side of the equation so that we have a 0 on one side and all of our other terms on the other side. I'm going to keep x squared positive and move 5x and 7 over to the other side of the equation. So subtract 5x and subtract 7 on both sides of the equation. On the right, we'll end up with 0. And on the left, we'll have x squared minus 5x. Then we have a positive 1 and a negative 7. So that leaves us with negative 6. To solve this, we can try to factor. Let's see, we need two numbers that will multiply to negative 6 and add up to negative 5. So 6 and 1 should work. And I want that term in the middle to be negative, so I'll give the negative to the bigger term. So x plus 1 times x minus 6. Solving for this is going to require us to set each factor equal to 0. When I solve the first one, I get x equals negative 1. And when I solve the second one, I get x equals 6. So this is saying when x is equal to negative 1, that looks about right. And then when x is equal to 6, somewhere up here, off of where we've drawn the graph, but if we were to continue eventually, when x is equal to 6, that's where these two graphs will meet. We can even check that we did this correctly by plugging negative 1 and positive 6 into both of these functions and making sure that you get the same output for both. I'll just do negative 1 for now. If we were to plug in negative 1, we get f of negative 1 is negative 1 squared plus 1. Negative 1 squared plus 1, which is 1 plus 1, which is 2. And g of negative 1 is equal to 5 times negative 1 plus 7, which is negative 5 plus 7, which is 2. Right, they do match, which means this is correct. These two graphs will intersect when x is equal to negative 1 and when they both have an output of 2. You'd have to do the same check for the other one, so plug 6 into both of these functions and make sure that you get the same output as each other as well. Okay. Now let's return briefly to our definition of a function. Remember, when we first started talking about functions, we thought about it as a map from one set to another. In the first set, the set of our inputs we called the domain of the function. In other words, that's the set of all x values for which that map, that function, is defined. In a finite function where they actually give you the map itself, it's easy to see what the domain is because they tell you, they show you. But if your function is given to you as an equation, sometimes you need to determine the domain yourself, just based on context. So you need to figure out what real numbers can I plug into this function that will make this particular function well-defined, so the output actually makes sense. Right? Well, let's look at the function f of x equals 1 over x plus 5. This function, when you plug in a variety of different numbers, start thinking through it. If I plugged in 0, I'd get 1 over 5. But if I plugged in 1, I'd get 1 over 6. If I plugged in 2, I'd get 1 over 7, etc. So it seems like a lot of different values are going to be defined here. You can even plug in decimals or lots of different irrational numbers. This is still going to be defined, except the only one single time where this is not defined, the only place this is not defined is when the denominator is equal to 0. That is, when x plus 5, that's the denominator of our fraction, is equal to 0. Solving this for x gives us when x is equal to negative 5. So when x is equal to negative 5, this is not going to make any sense. If I tried to plug it in, I'd have 1 over negative 5 plus 5, which is 1 over 0. And I know that that's undefined. That's not a real number. We can never divide by 0. And so the domain of this is going to be domain of f is going to be all real numbers except negative 5. We often write all real numbers using this fancy notation here. It's an R with like an extra line there. And so we could write all real numbers except for negative 5 by writing R with then a slash and then set notation of a negative 5. So this would be another way of saying that the domain is all real numbers except negative 5. And finally, one last way of expressing this is we could write it in interval notation. We could say all the numbers between negative infinity and negative 5, union all the real numbers between negative 5 and infinity. Okay, so there are 3 different ways of writing what the domain is. In words, in symbols with the all real number symbol, or in interval notation. So in general, when you're trying to find the domain of a function, you can use these rules to help guide you in finding out what this natural domain should be. If your function is a fraction, and it doesn't even necessarily need to have a 1 on top, it can have, I'll just put a star here, could have anything on top, we need to make sure that the denominator is not equal to 0. Right? If the denominator is ever equal to 0, the x values for that denominator being equal to 0 are not in the domain. So for this rule, we need whatever is in the denominator, that dot 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 part, to not be equal to 0. Okay, what about if you have a square root function? Square root of x, or square root of x squared plus 2, or square root of x minus 5? Well, square roots are only defined when the stuff underneath the square root sign is positive, or when it's 0. But it's not defined when the stuff underneath the square root sign is negative. So we need that dot 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 stuff to not be negative. We need it to be greater than or equal to 0. Should be 0. Alright? This is also going to be true for the 4th root, or the 6th root, or the 8th root, any even root. Right? Anytime you have an nth root for even values of n, Those functions are not defined when the stuff under the radical sign is negative, so we need that stuff to be greater than or equal to 0. Finally, for a polynomial function, f of x, the domain is always going to be equal to all real numbers. For a polynomial function, the domain is all real numbers. You can plug whatever you want into a polynomial function, and the output would be defined. Let's look at a couple of examples. F of x equals this polynomial function here. We want to find the domain of each one. Well, we had just said for a polynomial function, the domain is going to be equal to all real numbers. Always. Great. Couldn't be any easier than that. Number 2, it's a little more complicated. We have the fourth root of 1 minus x. Check that radical, right? Check what root you're taking. This is the fourth root, which is indeed even, which means if we go back to our last page, for an even root, we need whatever's underneath the radical sign to be greater than or equal to 0. So I need 1 minus x to be greater than or equal to 0. I can just solve this inequality by adding x to both sides. So I get 1 is greater than or equal to x. Or another way of writing that would be x is less than or equal to 1. So my domain is all x values that are less than or equal to 1. In other words, in interval notation, I want any x value that's less than or equal to 1. So that's going to be everything from negative infinity up to 1 and including 1. So I put a bracket on the 1 to indicate that 1 is included in the domain. That makes sense. If I try to plug in 1 here, 1 minus 1 is 0, and the fourth root of 0 is 0. So that's my domain here. Alright, third example, we have the cubed root of x squared minus 5. Just like before, check out what root you're taking. Is it even? No, it's odd. In fact, you can take an odd root of whatever you want. You don't have to worry about this. If it's an odd root, then the domain is all real numbers, provided the stuff underneath the radical sign is just like a polynomial, right? As long as you don't have a fraction or something underneath the radical sign. Alright, finally, this last function here is a rational function. It's a polynomial over a polynomial. Now, we know that anytime you have a rational function, the denominator cannot be equal to 0. If the denominator is equal to 0, then that number is not in your domain. So what I'm going to do is rewrite this as in its factored form. I can factor the numerator to be x plus 2 over x plus 1, and I can factor the denominator to be x plus 2, x minus 2. And you may be tempted to cancel these common factors in the top and in the bottom, but you shouldn't do that when you're looking for the domain. Because if we're trying to actually see where this function's undefined, we need to see where the entire denominator is equal to 0. Setting that denominator equal to 0 is going to mean that at x equals 2 and at negative 2, this entire function is going to have a 0 in the denominator, which is going to make the entire function undefined. So really what I should say is that for our domain, x cannot be equal to 2 or negative 2, because it gets zeros in the denominator. So our domain is going to be all real numbers except 2 and negative 2. And again, if you wanted to rewrite that in interval notation, you certainly could. Right? But we're just trying to say it's all real numbers except 2 and negative 2. Okay. Last thing we're going to talk about is finding the domain of a function graphically as well as the range. So remember what domain is. Domain is any inputs for which a graph or for which a function is defined. Okay? In other words, look at the x-axis and see for what x values does your function actually have an output. Well, in this first function here, for any x values less than negative 1, the function's not defined. We don't have any kind of a graph over there. It starts at negative 1, and then it will continue after that. That arrow is telling us that the function's going to keep going, the curve will keep going in this direction. And so we can say that the domain is all real numbers greater than or equal to negative 1. In interval notation, we can write that as negative 1 to infinity. In the second example here, if we started at negative infinity and start following it along, we do have a function up until we get to this point right here. At negative 3, we have a hole on this curve, and the function jumps up to this line up here, where there's also a hole. What this tells us is that f of negative 3 is undefined. There's a hole here, there's no output of the function here. That means negative 3 is not in the domain. But if we were to continue after that, we have all these x values that are in the domain, right? These are all in the domain here. Up until 1, and since we have a filled-in circle here, 1 is in the domain. Then we continue our function, and it looks like it's going to keep on going forever. So it looks like the only x value that's not in the domain is negative 3. That means the domain of this function is going to be all real numbers except negative 3. In other words, you could write that as negative infinity to negative 3, union negative 3 to infinity.